Hello?
Yeah, okay, thank you.
No problem.
All right. Let's so last time we left off in diagonalizability. Let's review the main result. So first, let me talk about the real case. So in your book, when you constrict your eigenvalues to be real, you need the following conditions. You need the summation of multiplicities to be the whole space, and you need each of the geometric multiplicities to equal the algebraic. In the complex case, where you allow the eigenvalues to be complex, you only need this. Can someone tell me why we get the first one for free? Here or in the Zoom people? You guys can speak up if you like. Okay, you can use the mic. It's easier if you like, or you can type. So why in the complex case we get for free the first constraint? That summation of multiplicities is the whole space. Wait. Yes. Oh no, you know as well. What about the other two? But, no, I'm waiting. Yeah, you guys can tell me.
Is it because like C is isomorphic to R2, so it's almost the same? Just a wild guess, but I don't know.
No. What do you mean the same?
I mean, I just thought maybe like because C behaves kind of like R2, it's isomorphic, so maybe that's why you get the complex case just from the real case.
No, it's the other way around. You get the. Okay, let me. No, but no. My question was not clear. I'm saying that. So you have these two assumptions here, and these two together imply diagonalizability. But if you allow if you allow your eigenvalues to be complex, you just need to check this. You don't need to check that they sum to the whole space. Was that real? So What do you guys think? Why don't I need to check summability? Okay, yeah. Right. Yeah. So yesterday we talked about this. So this is the characteristic polynomial, and these are the multiplicities. And the fundamental theorem of algebra says that if you have an nth degree non-zero polynomial, otherwise it's not nth degree anymore. It has exactly n complex roots. So, like equal, that means equal. And you count the multiplicity. So that's how you get that summation of mi is equal to n, which is the size of the matrix, right? Characteristic polynomial. By definition, is written in terms of a basis. So this is the n by n. But we proved a couple of weeks ago that the cardinality of the basis is an invariant. So it's always equal to the dimension. So that's the one. Right. Right. Okay. So yeah, I mean, this is the main result though. Like in practice, you are allowed to use complex eigenvalues. So you just have to check each of the geometrics equal the algebraic. That's it. The other one you get it for free. So it's free due to FTA. All right. Sounds like a government. So yeah, okay. But in general, they're not equal, but you still have this inequality. Let's prove that because the proof is interesting. And we will need it for the Jordan block in 2 weeks. So we can prove that geometric is always less or equal than algebraic. That's the result, and the proof is trickier than we think. So, by definition, geometric algebraic multiplicity is the highest power such that you can factor it in this form. Okay, so this is the largest degree. Largest degree possible. Okay, and G lambda is some function that's not zero at lambda star. So I might as well write lambda star. Okay. So how are we going to do this? We can factor the polynomial in a different way, where D is the geometric multiplicity. So let me write it in both ways. So we can do this dimension of E lambda star Q lambda. We're going to show that this is equal to characteristic, which we already know is equal to this. And from here, you might ask, why is this the largest? You can do Euclidean division, so whatever you like. But the point is, yeah, this M lambda star is picked to be the largest, so you require that E lambda star is less or equal than M lambda star. No? Okay, yes, question, yes. Oh, like, when I say the largest, if it's not the largest, divide again. So, yeah. Oh, because Q lambda, so how do you say this? Yeah, exactly. You click in division, so you have to. So okay. Here's how you do it. Okay, I have a quick. Suppose otherwise. Suppose otherwise. Then what you get? You get that G lambda is equal to lambda minus lambda star D minus. No, that's actually a good question. I wish I had thought. It's D minus M lambda and then Q lambda, right? Suppose contradiction. Like assume D is bigger or equal, strictly bigger than M lambda, right? That's our contradicting assumption. That means you can write this, but then you can put lambda equal lambda star, so you get 0. But the G lambda star by assumption is not 0. Yeah. All right. Yeah, so the meat of the proof is to show this. And we have to use Jordan blocks, which you will see in 2 seconds. All right, what do? We start with the basis. This is an eigenbasis, but for a fixed eigenvalue. So TV1 is lambda star. V1 to the TVD star D. You use the augmentation lemma to get a full basis for V. Okay, so you have V1, VD, and then you add other stuff that are not necessarily eigenvalues. It's just vectors, linearly independent of the other stuff, right? Because you need to span the whole space. Perfect. So we don't know what they are. I mean, they're just, yeah, we don't know. Like VT plus 1. No idea. Right. Okay, so let's do this. So we have to compute the characteristic polynomial. This is the characteristic polynomial. And I will prove that this is equal to minus lambda lambda star to the dimension of the space times some polynomial. Okay. So I know the proof will be technical, but let's take a breath and because we will see this again in 2 weeks. So this is a good time to do this. Right, so this is the definition of being an eigenvector. I mean, yeah, okay. So I think that's okay. And let's see how we use this. All right, here I have to remind you some stuff. So how do we compute this? So T minus lambda I B. Can someone tell me how to compute the first column? You can use the mic if you want. So yeah, how will we compute the first column? What's the definition? Do you know? No, but by definition, forget about all this. What B is specific. You don't have to give me the final answer. Just what's the definition of the first column? Yeah. The vectors of what? Yeah. So what should I? What do I? Yeah. Can you tell me specific? Not the value. Just what do I write? T minus lambda. Evaluated. Like yeah. What's exactly the situation? The first column of B. Well, I mean, if that confuses you, let me just write S. So what should I, in general, if you have a transformation, how do you find, yeah, okay, go ahead. So then what should be the first thing here? Okay, so let me say what's going on. So yeah, let me write. Any comments from here? Lambda star is just an eigenvalue. Kelly, you guys can use the mic because I forget to check uh, the applied basis to V1. Okay, I guess people kind of, we have to use the coordinate maps, right? That's all I wanted to hear, to be honest. So you, right? So you have to go down to your original space. Like V gets mapped to R of dV, right? From gamma B. So the first column is what? You evaluate, like you guys said, lambda I at V1. And you compute this, I mean, it's fine. You write it in terms of the like A1K of VK. I think people understood that. But then to get the thing, you need to extract the coefficients. You already met that or not? Which you do through gamma B. So you act with gamma B, and it gives you a A1, A1N. Oh, did I make? Yeah, that's right. I just have to flip the thing. It's K1. Is that okay? Everybody follows? I mean, you can't just put a vector, like these vectors could be polynomials. What does it mean to put a matrix of polynomials? You have to extract the numbers. Okay. All right. So now let me ask you this. What is this actually for? Let me call this, yeah, what is T minus lambda I of VI for I1 to D? So you do the same thing. But this is actually what? It's actually clean, super clean. Anybody knows? Yeah, go ahead. Yeah. So you have T of VI minus lambda VI, and this is lambda star lambda VI. So this is, so going back to our matrix, if you take gamma B of this, you just extract this guy. So you have lambda star minus lambda, 0, 0, 0, 0, 0. Like for the V1 case. Then V2 case, what do you think? I just want to see if you understood. Yes. No, like what would be the second column? Okay, I just want to see if we go forward. So, all right, and you play this game up to you play this game up to TBD. I mean, T minus lambda I VD. After that, you have no idea. So you put a matrix A and another matrix B. Because you don't know what the columns are. And So up to here, you have D times n minus D. In this case, n minus D times n minus D. Okay, so you have these block matrices. Again, this is D because you have D vectors. So you get D coefficients. And then this guy over here is just a huge zero matrix of size n minus D times how many columns? Huh? Yeah. Perfect. Questions? So are we saying, can you use the mic? Because you have good questions. So are we saying that basis B as V1? No, not no. You have to evaluate the map, right? So T minus lambda at V1 is just T minus lambda I at V1 is just lambda star minus lambda V1. So that's why we get this. You have to add with the map. Is that okay? You can let me know.
I'm still a bit confused, if you can hear me.
Yeah, I can hear you. What are you confused on how we got the column?
Yeah, how we got the columns, how it's always like lambda star minus lambda and zeros around them.
Yeah. So V up 1 is an eigenvector, right? Right?
Yeah.
So then T minus lambda I of V1 is TV1 by linearity of V1, right?
Yeah.
So this is lambda star V1 minus lambda V1, right?
Wait, is it lambda star v1 or just lambda star?
Huh? Yeah, lambda star V1 minus lambda V1.
Okay.
Is that okay?
Yeah, wait, because lambda star is an eigen. Sorry, what is it again? It's an
Yeah, so you start with the fixed eigenvalue. So
Yeah.
we start with the fixed, I mean, I could have called it lambda 0. I don't know. I couldn't think of a good name. So we start with the fixed eigenvalue. We study E lambda star, and this is the span of V1 to VD. So it's one eigenspace that is spanned by multiple vectors. Okay?
Yeah. Okay. Yeah.
All right, so here's the matrix I just explained. So you have the identity matrix upstairs, and you have two block matrices. This, and I mean, if you don't understand what we do next, it's fine, because we're going to come back to it with Jordan blocks. But this is an appetizer, okay? Just an appetizer. So don't worry, you won't see it in the midterm. Don't be scared. So we have to compute its determinant, right? The determinant of this is the characteristic polynomial, right? And I think you can already see that we can extract some product lambda to the power of d, because there's d of them and they're on the diagonal. So you can kind of see already how we're going to get the thing we want. All right, let's go. So this matrix is diagonal, just the identity matrix. So here's a nice trick, which I will do again in 2 weeks. So don't worry. It turns out that you can factor this matrix into these two matrices, and you can do it by hand if you like. So you pretend that this is a 2 by 2 matrix, and if you do that, you will get exactly that. So pretend it's 2 by 2, okay? pretend 2 by 2. So if you do this, you get the guy on the left. Okay, so this is a question you can answer now. So what's the determinant of the second 2 by 2? You guys on the chat can answer as well, if you know. So what's the determinant of this? There it is. Yeah. So in general, any upper triangular matrix, A, B, C, blah, 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 with stuff, doesn't matter. If you take its determinant, you just get A times B times C. Yeah, but if you arrange them, they're like, I mean, yeah. Yeah, you have to visualize like a n by n matrix. Yeah. All right, so second block is easy. So we have to find, we have to compute the first guy. All right, so I know I will just define the determinant as this. So let me explain and we'll come back to it. Okay, so if you have a matrix M, you can, it's actually a proof, but I think Camelia will put out a note. Okay. So what is this formula? How do you use it? Let's do 3 by 3. 1, 1, 2, and put a bunch of ones. Put a 0. No, too many ones. All right. This is M. So what does it say? It says take. So let's do I do first row. Okay. So so determinant of M. You take the first entry and you remove first row, first column. This guy here is called M11 because you remove first column, first row. So you have 1 times M11 plus 1 times, you remove this and this, but this will be 0, right? But I can just write it. So 1, 2. And then finally 1 times 0, 0, yeah, M13. And okay, yes. No, this is the permutation one. Yeah. So, but okay, these two both die. So you're left with the M11, which is this guy. Okay. And so you did get the 1 times 2, the variable. So 1 times 1 times 2. Okay, this is the formula. And you have to prove it with row reduction, and it takes a while. So. All right, okay. So I just want you at least to see it once here before you see it again in the world. Like, it's crazy that you haven't seen this. I mean, like, I mean, you will see it. I know. I've seen it before. All right. Fine. So what am I doing here? Yeah, I'm gonna apply this to compute this, and it's pretty beautiful. So you have this lambda star lambda, lambda star lambda with zeros, and then you have a 0 here, and then you have B. So here's how you do it. You do the same trick. You remove first row, first column. So you get lambda star minus lambda. And then the rest, some determinant M11. But the other ones are all 0. So you have a bunch of zeros. Okay? That's the first iteration. And you play this game again. So you play this game again for this guy. So you again get lambda star minus lambda of this new reduced matrix. So let me show you the reduced matrix, M11. So it's almost the same. Zero, zero, zero. But here you have D minus 1. Here you have D. Because you killed the first row. So this is M11. So you play this game again. You first row, first column, and you end up with the determinant of the smaller guy. We call it M tilde 1, 1. Okay? Now we have the smaller matrix, and you remove its first row. And you keep playing this game till you hit this checkpoint. So you end up with D of them times times the determinant of B. And that's game over. So you call this guy Q lambda, and you get your exponent. Okay, so if you didn't follow, it's fine. We'll come back to this with Jordan blocks. This is really the neat. You gotta keep computing determinants there. And yeah, so we'll come back to this. Okay. If you have a question, please let me know. So that's it. All right. So why are we doing so what's the plan for the next 2 weeks? We're gonna prove a thing called the spectral theorem. Or if you have a, please tell me, what's the question? No, can you tell me the question, please? How do I get the first? Oh, yeah, let me do it. Let me do a 2 by 2 case. Lambda star minus lambda, lambda star minus lambda, 0, 0, some matrix. Yeah. How does this cofactor work? You remove first row, first column. So this is lambda star minus lambda times the remainder, 1. And then you look at the second guy, but this is 0 times M12. And you do the same. 0 times M13, and then the last guy. 0 times M14. But these guys all die out because they're 0. Is that okay? Yes. Oh, yeah, we did this before you came. So we, what was it? Yeah, like when we computed this characteristic polynomial, you compute the first entry, and the first entry is just like, how do you compute this, right? You compute it on V1, the first column, and you write it in terms of the other ones. But this is an eigenvalue, eigenvector, so you get lambda star. Yeah, the plan for the next 2 weeks, 3 weeks, spectral theorem and Jordan blocks. Spectral theorem basically says that if you have a matrix that is symmetric and it has positive eigenvalues, I mean, yeah, we'll come back to this. But you have positive eigenvalues. That's one interesting formulation. You can write it in Q, D, Q. So you, instead of P inverse, you can write it as some orthogonal matrix. This is called orthogonal. So we'll get back to this. This shows up all over the place. That's the whole point of this course. Spectral theorem for general vector spaces. All right. Now we're going to need a lot of technology to do this. And we have to start with inner products, which are interesting again for themselves. So up to now, we have vector spaces. We give you some vector, but from 2 to 3, you could say a lot more. You could even compute the length of the vector, right? And but what's the length of minus x plus x squared? So how do you compute length even of polynomials? There's a way to do it. So yeah, you know the familiar stuff that you have some basis and you project to that basis to compute the length. So we have the same idea. So you have something like minus x squared, and you project it down to your basis elements. So it would be like your x squared, and this is like, what is it? I don't even know. But you can map it. You can basically, let's say this is a 3. So the length of this guy would be 4. All right? Because you basically like add the coefficients. This is similar to the length of minus 1, 3, which is again, yeah, let me put square root 4. Euclidean distance. Maybe I'm mistaken. Okay, maybe my math is, oh, I'm sure my math is correct. Okay, so I want, I'm thinking of weird stuff. What am I thinking? Oh, yeah, square root 10. Yes. Yes. Okay, anyways, we'll get back to this. Let me not say nonsense. But there's a way to make sense of it. And the intuition I'm trying to convey is that you have to use the basis. Oh yeah, you have to pick your coordinate system. Otherwise, you know. Yeah, well, yeah, like right. So that's another. This distance we're gonna build is invariant. Yeah. Yes. So perfect. That's a great question. So yeah, sin x, ex. What's the length? What's the distance? Makes no sense. How do you compute it? All right. Let's talk about inner products. So if you take physics or mostly physics, in probability, if you're in statistics, this is called the expectation of xy. So whatever you like, covariance, this is all under the same group. And bracket, less bracket, this is all from physics. This notation. All right, so you need the following 3 properties to have an inner product space. First, you need this map to be positive definite. So let me give you a concrete example so that you don't have. So take V to be R2, and the standard inner product is just the dot product. Okay, so let me remind you, this was x1, y1, x2, y2. So you keep that in mind. That's the guy we're working with most often. And yeah, if you compute x, you get x1 squared, x2 squared, which is 1. And if it's equal to 0, if you have equal to 0 here, you need both of them to be 0. So indeed, x is the 0 vector. I mean, this is not a proposition. These are, I'm not proving anything here. I'm just saying what the axioms are. Second axiom is you need bilinearity, almost bilinear. It's almost bilinear because you don't have linearity, and so I shouldn't have written this. I meant B over here. So let me rewrite it. So I have AV plus U and BW. And the linearity statement is AV A B conjugate VW and then B conjugate UW. So in other words, you only have linearity on the first slot. This is called the first slot. And you have conjugate linearity in the second slot. We'll explain why you need this in a second. That's the situation. When we come back to norms in like 2 slides, you will see why I need the conjugate. Because I need to take square roots and I need things to be positive. So, okay, let me say it here. We need that B star is equal to this from complex numbers. That's why this comes out here. Because then I want to take square root of this. Okay, so we'll come back. Okay, so you need almost bilinear. And right, then you have conjugate symmetry. So when you flip your entries, x, y, you get yx. So again, let me remind you conjugate. People forgot maybe. So this is a plus ib, and the conjugate is what? Yeah. And our field will be the reals or complex. You cannot put the finite field. Yeah. What's the conjugate of a finite field? So now you see why we are all interested in these two. Yeah, so if you manage to build this amazing map, then you call V an inner product space. So Rn is an inner product space because you can just use the dot product. Okay. As an inner product. No, you don't have multiplication. You have scalar. Yeah. Anyway, so Rn is an inner product space. Inner product space. All right. Yeah. So this is the one in Rn. I already talked about it a little bit, but let's play with it a bit. So you have x. Let's do the first axiom just to give you some practice. So this is x1 squared, xn squared, and this guy is, if you set this to be, well, it's not negative, but if you set it to be 0, you force them all to be 0. So positive definite, it's good, you have it. Let me not go through all the analysis. This is usually the trickiest part. Like the linearity is kind of obvious. If you want me to do it, just come. Right, so you're going to see this word if you go in physics called Hermitian inner product. And this is when you want to define an inner product over Cn. So let me do C2 just to play with it. So, and let's do the positive definite again. Let me write Z because that's what people are more comfortable with. So you have, what is it? We have Z1 with itself, but conjugate. and Z2 with this. And to be clear, Z is a complex vector. Okay. Now, how do I show that this implies that Z is the zero vector? I just want to see if people follow. You can use the mic if you want to. People. Yes. Oh yeah. No, wait. No, the other guys. What do you think? Yes. What is this first guy equal to? So this is Z1 and this is Z2. Right, yeah. So this is A squared plus B squared, then C squared plus D squared. And if you set this to be 0, each of them needs to be 0. Okay, so A is equal to B is equal to C is equal to D. 0. All right, so you have positive definite. Another big application of this stuff is called quadratic forms. Again, I know them from probability. And optimization, actually, I remember. So, yes. So, stuff like this are also inner products, meaning you can put any matrix you like. So you have x1, x2, some matrix A, and then y1, y2 transpose. Right? So, my transpose mixed up. Maybe it's okay, so, right, so let's play with this. Let me show you at least a positive definite. So 1, 2, 0, 1, and then same guy. Let's do this. I just have to multiply things out. So I call this to be 0, and I want to show the 0 vector. So first, here is what? X1, X2, and then 2x2. And then you multiply them together. So, yeah, okay, well, so this is x1 squared. Yeah, whatever. X1 squared, x1, x2, and then x2, x1, x2 squared. Okay. This coming just a second. And then, right, 2x2 squared for this. All right. Okay, what did I want? Right, so you set this to 0. Unless I made some mistake. Yeah, and from here you can show that x1 is equal to x2 is equal to 0. This kind of okay, I'll do it later. Let's do it. So this is x1 squared plus 2x1 x2 plus x squared, and then minus x1 x2 and then plus x2 squared. This guy is the full thing, and this guy you factor out with this. thought I had this. All right.
Sorry, Prof, how do we get
Yes.
to this? How do we get to the bottom line on the screen?
Oh, this is the assumption. So we want to show positive definite, and yeah. That's all. So we want to go from here. We want to show that these two are both zero. So I thought I had.
No, I mean, like, how do we get the x1 squared plus x1 plus x1 x2 plus 2x2 squared equals 0?
Oh,
Like,
so
in the
here,
base.
right. So here you just multiply out the. Maybe that's better. So you have to multiply this times this vector, which is just the dot product.
Oh, okay. I was just confused because it was like vertical. Okay.
Huh?
I was just confused
No,
because
these are real numbers. Yeah. Okay, I'll continue this thing. Okay, so that's fine. Let's just continue next time.
Hello, Professor.
Yes.
It's just about a small thing in assignment 3. It's about how some terms are written. I'm struggling to understand the difference between P and R and PR.
Yeah, PR are all the polynomials of any degree, finite degree.
Yeah.
But PN are all at most n.
Oh, like n can go to infinity, right?
No, n cannot go to infinity. N is always finite, but it's always a finite number.
Always a finite number. Okay. And last thing, in the homework, I see a notation about the kernels. Like, for example, ker T belongs to ker Ti belongs to ker Ti plus 1. The symbol of belongs, there's some sort of line that crosses the.
The sign of, sorry, what? The sign of what?
You know the sense of like belongs. The string of belongs.
Yeah, it's this E guy.
Yeah, the E. Sometimes it's crossed under the E.
Yeah, it means that it doesn't belong.
Oh, it means doesn't belong? Okay. I see. Thank you. Have a nice day.
Yeah, go ahead.
I had a question about
Sorry, Prof. Can I ask one more question?
Yeah, okay, no, just like, yeah, I'll be in a second. Yeah.
Okay.
or am I wrong?
I have no idea. I don't know the solution. I don't know. I don't know. Man. Yeah, try to prove it and no. Actually, always try to disprove it. Then you will get an idea if it's true or not. So instead of trying to prove it, try to disprove it. Try to show that no such path exists. And then, yeah, like, and then if you're unable to prove that, there will be a map, yeah. Yeah. I mean, I did this in class. Exactly. This is called the coordinate.
but there's a
Yeah, this is called the coordinate. I solved this. You can look at my notes. I have it. I have the solution. You can look at.
okay. Thank you.
Yeah, go ahead. Go ahead. Hello? Somebody
Yeah.
had a question. Yeah.
I had a question. So, on the slides here, when you write x1, x2 with the t, does that mean that it's supposed to be horizontal?
It means I probably made some fudge. It has to be transposed. So yeah, horizontal, like over here, right? Huh?
Okay, okay.
Is that okay?
So when you write the t, it's what do you mean by transposed? It's just horizontal or like
Yeah,
it
yeah,
shifts?
right. For matrices, it's kind of complicated, but for vectors, it just means you flip it down.
Okay.
Yeah, because
Thank
yeah, okay, cool. Yeah. What is what? What? Sorry, what? The V, how conjugate? Oh, yeah, it's itself. Because a real number is of the form what? Yeah, yeah, yeah. No. Yeah. Yeah.